Hi. Weaving baskets and braiding hair for quantum computing. That's me. In my job, I work on understanding the mathematics of quantum computing. If you had to choose between a course in basket weaving versus a course in quantum computing, which one would you choose? It sounds like basket weaving is going to be the easy one, but it turns out that basket weaving is not so easy. And actually, we are using some of these ideas to build quantum computers. Weaving and knots and braiding has a lot of history. Kelvin had this idea in 1867 that atoms were actually knots in the ether. That turned out to be a random guess that was wrong, but it inspired further work into classifying and understanding knots. Later in the 20th century, knots and braids made a reappearance in physics. Now modern physics is using the mathematics of braids to understand how particles called anyons behave. It's very advanced algebra, but my hope is that I can avoid all of the complicated calculations and still give some idea of what this is all about. Let me start with a riddle. What stays the same even when you change it? Imagine you go to the shop to buy some cherries. You ask for 3 cherries. You don't care which 3, any will do. All the cherries are the same. If you don't have numbers in your language, you would have to point at exactly which cherries you want. This is the magic of numbers. They make the counted things the same. You also don't care which order you get the cherries. There are 6 ways to order them, but it doesn't matter to you. This is how numbers work. They forget how to order the cherries. Can swap them around. It's the same 3 cherries. Can swap them again. Same. Swap the cherries. Same. Swap. Adding numbers together works like this as well. We can change 3 plus 5 into 5 plus 3 and get the same result because the order doesn't matter. This is an important theme of modern mathematics. We don't just write 3 plus 5 equals 5 plus 3. What is the process that changes 3 plus 5 into 5 plus 3? There's more here if you look closer. For example, how many swaps did we need to use here? We invented numbers thousands of years ago for describing how different things are somehow the same. 3 cows, or 3 beans, or 3 cherries. But if you look closer at the cherries, you will always be able to find some variation, some distinguishing marks, some slight differences in size or shape. The universe knows these cherries are not all the same, even if you don't care. Swapping cherries around changes reality. It changes the universe. Is there anything in the universe that does act like a number? Can we find or make any kind of perfect copies of anything? The answer is yes. When we discovered quantum physics in the 20th century, we found identical particles. These yellow balls are particles called bosons. They don't really look like this, but at least with this picture you can see where they are. And when you swap these around, the universe doesn't notice. Reality has not changed. We need a way of writing quantum mathematics. There's one main rule to learn first. Here it is. If something can happen, then put a ket around it to make a quantum state. You put the thing that happens inside the ket, and then outside the ket is the quantum mathematics. For example, take some cherries and put them in a ket. We don't usually do this because cherries are way too complicated. It makes more sense to put particles in a ket. Here's 3 identical bosons in a ket. I put letters on each boson just so we can see where they move to. The letters are not real. These bosons are all identical. When we swap them around, the kets are equal. After every swap, we just get back the same quantum state. The universe doesn't notice our swaps. Reality is the same after each of the swaps. You might ask, how do we know the bosons really are the same? Maybe it is like the cherries, and we just didn't look close enough. This is a good question. If we didn't have identical bosons, then lasers just would not work. But this is a story for another time. There's another kind of particle called a fermion. Here I made some green balls to represent fermions. When we swap two identical fermions, the quantum mathematics is a bit more tricky. First, we need to remember how to multiply with negative numbers. The rule is a negative times a negative is a positive. Just like saying a bad thing done badly is a good thing. The other rule is a negative times a positive is a negative. Just like saying a bad thing done well is still a bad thing. So every time we hit this with a negative, the sign flips. The good thing becomes bad. And then the bad thing becomes good again. And it just keeps going on like that. Now we're ready for the quantum mathematics of fermions. Here's how it works. When we swap two identical fermions, the quantum mathematics says that we times by -1. Every time we swap two guys over here, the sign flips over here. -1, swap, +1, swap, -1, and it keeps going on like that. There is a deeper story here. Just like when we swapped cherries around to make 3 + 5 into 5 + 3, we discovered a process. We can do the same here and study the process that swaps particles around. This process takes place in a three-dimensional world. Here we swap two fermions. If we do a swap-swap, one fermion goes all the way around the other one. We can see this more clearly if we follow one of the fermions. The other guy just goes all the way around. That's a swap-swap. Now let me show the path taken in blue. Swap-swap. Notice that this blue path is near to another blue path. I just moved it a little bit. And that path is near to another one. I moved it a bit more. And that's close to another blue path over here. And here's another one, just moved a bit more. It's getting smaller and smaller every time until really we don't need to move this guy at all. So what does that mean? It means that swap-swap does nothing. Swap-swap equals nothing. This is an equation between processes, not just an equation between kets. Here's a summary of what we found so far. Swapping identical bosons does nothing. The kets always stay the same. Swapping identical fermions multiplies the ket by -1. What happens when our particles live in only 2 dimensions? These particles are called anyons. I'm going to draw these in purple. Now let's take one anyon around the other one, just like how we did this with fermions, but now we have only 2 dimensions to move in. There's no way to retract this blue path. It gets stuck going around the central anyon. We need the 3rd dimension to pull this blue path over, and we only have 2 dimensions now. So this time, swap-swap doesn't need to do nothing. Let's use the 3rd dimension to show time, and I'll repeat this swap-swap process. The anyons are still moving around in 2 dimensions, and we are using the third dimension to keep a record of the path. You can see this path becomes a braid, and we can't undo this braid. It gets tangled with itself. This is a swap of anions, but we can't undo it. Now the quantum mathematics, it looks like this. Except there's a question mark. The algebra is much more tricky, so I'm not really going to talk about that. But we can work out what is this question mark in some cases. For example, if we do a swap and then an unswap, we know we should be able to undo it and get back to nothing. So that's one equation. And we can always undo whatever swaps we do just by doing the unswaps of the swaps in the reverse order and get back to nothing. Swap, swap, unswap, unswap. So that's another equation. And there's all kinds of equations we could make here. Swap, 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 unswap, 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 unswap. Actually, all of these equations come from this basic identity. Swap, unswap is nothing. Here's a more tricky equation. We can't undo this to nothing, but we can slide the swaps around, so these two processes should be equal. Just like how we started wanting to show why 3 plus 5 cherries is the same as 5 plus 3 cherries, and this led us to think about the process that makes 3 plus 5 equal to 5 plus 3. Here we are showing two processes that are equal, and we are showing a process between these processes that makes them equal. This kind of reasoning is called topology, and manipulating anions this way, we hope to make a topological quantum computer. This is from the April 2020 issue of Science magazine. Research groups from all around the world are working on building two-dimensional materials where anions can live. We will have to wait and see how this goes. That's all for now. Thanks for listening.